recording. So I'm recording this session. Please let me know if you have any problem or an issue with the recording. Otherwise, I'm assuming that everyone is fine with recording this file and share it online for the use of the class and for this class. As we discussed in statics, we are looking into relationship between forces when our robot or our mechanism is not moving. So just relationship between torque and the force. Torque we produce or we apply to the joints, and the movement of the end effector, well, not movement, the force at the end effector, when it's fixed, it's forcing something back or trying to move something, but there is no movement, just exchange of the forces and torques. To have a better understanding of the robot behavior, we definitely need to look into the dynamic of the robot as well, because our robot is doing some mechanical work, and this mechanical work means involvement with movement, with force, with speed, with acceleration, with mass. And when I have all this together, definitely my equations will be different, slightly more calculation, and we also need to have a better understanding of relationship between these different parameters inside our robot to understand what our robot is capable of, or what kind of limitations in terms of mechanical force and movement our robot has, and how these limitations or these capabilities are related to the structure of our robot, to the force we are applying, to the torque we are applying to the joint, or to the motor we have chosen for our robot joint movement, or other source of energy which we have in our system. So these relationships are required to have a better understanding. And even if you think, if you are not a robot designer, which you definitely, if you design a robot, you need to have this understanding, if not detailed calculation, but you need to have the understanding and simulation of the behavior of the robot. And as a user, you can make sense of why something happens or why behavior of the robot is like this. And to design a control system, you definitely need to have a model dynamic of your robot. Okay, just a basic review again. We did this before, but I want to make sure everything is clear. Regarding the Jacobian matrix, the relationship between the velocities of the robot endpoint and the joint velocities, rotational velocities, obviously, is obtained by differentiation. The coordinates of the endpoint are functions of the joint angles, which in turn are functions of the time. Okay, which is true. It says that your end location x, which is a function of theta 1 and theta 2, and these theta 1 and theta 2 themselves are functions of time. So you can say that my x is a function of theta 1 t and theta 2 t. This is basic representation of relationship between x in the coordination system and theta's joint angles. Same goes with y, which is a function of theta 1 t and theta 2 t, a function of something which is a function of time itself. Well, in basic mechanics, we remember that if I have position x, my velocity will be derivative of that position. It's kind of this course in physics of mechanics of movement. And if you're looking for acceleration. You know that acceleration is a derivative of speed, which makes it second derivative of location. And since I'm going to talk about force and dynamic and movement, I know that the force I need to accelerate a mass of m with acceleration of a is calculated like this. And I also should remember that all of these are vectors. So if x is a vector, v is a vector, a is a vector, so on and so forth. Okay? So keep this in mind from your basic fundamental dynamics or physics of mechanical movement. All right. So if I want to do similar to physics, in which I had a one-dimensional x, I'm looking to find v, like a derivative. My question would be, what if my x is something like x and y v is like vx, vy? Can I build up a relationship like this? Derivative of location gives me speed. The answer is yes and no. Yes, because yes, still we can find a relationship with derivative, but it's not as straight as this. Why? Because your x is a function of two parameters, theta 1 and theta 2. And each parameter itself is a function of time. So in math, we know that if you have one-dimensional variable, like if I had f of theta, which is function of theta, and theta is not function of anything else, therefore prime, which is d theta to dt. But I know that if I have a function of theta 1 and theta 2, in that case, my derivative will be different. My derivative will be the function of the derivative of f according to theta 1 and derivative of f versus theta 2. I have to have them both together. Okay? And when my function, like what we have here, is two-dimensional itself, it has two values like x and y, and two inputs. What are dealing with is a function with theta 1, theta 2 as inputs, and x and y as outputs. And also, we know that these theta 1, theta 2 are functions of time. So derivative in this case is rather complicated compared with the original one, or we have to think bigger actually. We have to think in two or more dimensional to be able to write that. And that's how we end up to Jacobian matrix. Jacobian matrix actually can be built up as this. So if you are looking for derivative of x and y, each one function of two other parameters, what you need to do is your x derivative will be derivative of x versus theta 1 plus derivative, times derivative of theta to time. I'm going to write it here with more space, otherwise I need to wrap it. So x dot derivative of x or dx to dt, how x changes over time depends on how x changed with theta 1 and how x changed with theta 2, and also how theta 1 changed with time and how theta 2 changed. So makes sense, right? So how x changed with time depends on how x changed with theta 1. the partial differential. That's why we write E like that, theta 1. How theta 1 change with time itself, plus how x changed with theta 2, and how theta 2 itself changed with time. This is for x. For y, same thing. For y, dy to dt, how y changes over time depends on how y changes according to theta 1 and how theta 1 changes over time, and how y changes by theta 2 and how theta 2 changes by time. So equal round y to round theta 1 times d theta 1 to dt plus round dy to d theta 2 times d theta 2 dt. If you write this in a matrix form, that's what you get. That's what you get. Dx to d theta 1, dy to d theta 2, dx to d theta 1, dx to d theta 2, dy to d theta 1, and dy to d theta 2 times theta dot theta 1 dot theta 2 dot, which are actually d theta to dt theta 1, and this one is d theta to dt. That's how we define Jacobian matrix mathematically. And this Jacobian matrix is a kind of essential component in multidimensional system analysis. So it's not just robot. It's not just something we just got trapped by this math calculation and it just discourse. No. Whenever you have multidimensional system, means a system with several input and several output, and you want to make a mathematical analysis, it's very likely you end up with Jacobian matrix. Jacobian matrix is kind of extension to normal derivative, normal differentiation into multidimensional systems. Okay, in system when you have multiple input, multiple output, and each input itself is a function of time. They're changing over time, and they affect each other and create outputs. You need to use concept of Jacobian matrix. You need to have this concept in our case. So when I had two-dimensional robot, I remember that there was a relationship, if you remember in my calculations, between x endpoint, between endpoint and theta. Review the previous slide. You see, we found this relationship. We found this relationship between x, y, and theta 1, theta 2 from one side to the other side. Okay, and you have this relationship from which you can find the Jacobian matrix. First component of the Jacobian matrix, this component is derivative of x versus theta 1. So this one is the derivative of x theta 1. Do that to see derivative of x versus theta 1. So here I have cosine becomes negative sine, this one. And I have this becomes negative sine of theta 1, theta 2. So that's why you get this. This component is dx d theta 2. D theta 2 is easier because this one is not function of theta 2. So derivative of this versus theta 2 becomes 0. And derivative of this versus theta 2 becomes negative sine theta 1 plus theta 2. That's what you have here. Same with this one. This one is actually dy d theta 1. dy d theta 1. In this one to the theta 1. derivative of this one versus theta 1. Derivative of sine becomes cosine. So will be L1 cosine of theta 1 plus derivative of this one versus theta 1 becomes L2 cosine of theta 1 plus theta 2. And that's what you have here. And the last one is dy d theta 2. This one, again, sorry, this one, derivative versus theta 2. Sine derivative of this versus theta 2 becomes 0 because constant, sine of theta 1 is constant for theta 2. Theta 1 and theta 2 we are assuming are independent. Means derivative of one of them versus the other one is 0. No change. No relationship between theta 1 and theta 2. But here, you have L2 sine of theta plus theta 2, so will be L2 cosine of theta 1 plus theta 2. That's what we have. So you see there is a concept, mathematical concept beyond Jacobian matrix. What we introduced as Jacobian matrix initially was based on our understanding from what happens between velocity at the endpoint and rotational speed or velocity of the joints. Okay, but it comes from a stronger background when you want to do a multidimensional system analysis. Any questions so far? No question? So one of the exercises I want you to do and I will ask you to do is to be able to calculate Jacobian matrix if I, well, just as a scale, not related to here. So if I give you a relationship between x, y, z with three parameters, let's say theta 1, theta 2, theta 3. So as a function of theta 1, theta 2, theta 3, and a g of theta 1, theta 2, theta 3, and FGH of theta 1, theta 2, theta 3. So it is three-dimensional. I have three inputs. I have three parameters on which our parameters depend, okay? So in this case, you can again build up a Jacobian matrix, which would be 3 by 3. First component of the Jacobian matrix of this example will be derivative of f versus g theta 1. Second component will be derivative of f versus theta 2. Third component of the first line will be derivative of f versus theta 3. Second row will be same thing for g function. Will be derivative of g theta 1. Derivative of g theta 2. And so on and so forth. You build you can build it up as we need for this example. So finding Jacobian matrix, if you have relationship between input and output of a multidimensional system, then it's a basic skill which is super easy, like what we did here. Simply you can use that, you can apply that to any dimension, any system with any dimensional. Okay? Any question? No question? Good. Very good. So the relationship between the joint velocities and the velocity of the endpoint is obtained by inverting the Jacobian matrix. That's what we did. Okay, I'm reviewing briefly what we did in more abstract form. So relationship between the velocity of the joint rotational velocity, which is a function of theta 1, theta 2, or whatever we have, and position, location of the, or coordination of the endpoint is based on inverse Jacobian matrix. Why? Because I had x equal Jacobian q. And from there, we found this relationship between speed at the endpoint and speed at joints, rotational speed or velocity of the joints. We had this. To make inverse means if you know how much speed you need, to produce a joint, you need the inverse Jacobian matrix. And inverse matrix, as I said before, for two-dimensional is for 2x2 matrix is super easy. You just have determinant of the matrix here at the bottom. It's not positive, you know. This is the determinant of A. What you have here is of A. Okay, and just replace these two and negate these two. So these two will be negative. These two will be replaced. Just simply you get your okay. So for two-dimensional for a robot with 2 degrees of freedom, there is no excuse that I can't find the Jacobian matrix or inverse Jacobian matrix. You should be able to do that if I give you numbers. If I give numbers, you should be able to do it pretty simple with calculations. Okay, and that's what we found for what we had before for our 2-segment robot. We could write this, and when the manipulator is close to the singular poses, when the angle theta 2 is close to the 0 for the simple tube robot, the inverse Jacobian matrix is ill-defined. It's not well, when determinant is 0, actually you get division by 0. That's why you find something. Your robot might do something which you don't understand, you don't expect, you don't want to. Inverse Jacobian matrix is ill-defined. We shall make use of Jacobian matrix when studying robot control as well, as I mentioned later. Okay. Brief review on what we did on a relationship between Jacobian matrix and also the static relationship between forces, exchange of the forces, and torque. Torque we apply here and we apply here, and the forces which are decomposed into 2 directions, creating 2 torques on X and Y. That's what we call torque on Y, and this one was torque on X. It was X times Fx, and this one was Y times Fy. And what is Y? This is Y. I'm sorry, this one was X. Mistake, sorry. This is Y, and this length is X. That's what we did. And based on it, we calculated the torque we need M1 for this, and the torque we need at M2. And again, writing that in terms of matrices gives me a relationship with the famous Jacobian matrix again. The Jacobian matrix comes in again, but in transposed form. In transposed form, here the relationship between force and torque. How much force I need, how much torque I have to apply, how much torque I want, how much force I want. We want this, then it means we need this at our motor. So when you're designing a process with your robot and you expect your robot to apply force on a curve at a value, you can calculate the required torque that you need to apply through your motors. Can they produce that, or how much, other calculations based on energy conversion system you're using for your robot. Any questions so far? I'm going to change the discussion. Any question? No? Okay, so let me ask the same question I normally do. So on the scale of 0 to 10, how difficult is robots study of robot static. Give me your evaluation, how difficult it is. What we talked about, the force and the static angle and the distance. Nikita says 10. Is it that difficult, Nikita? Paul 5, Milton 7, Lou 7, Nasir 6, Alex 6. It all comes out higher because Nikita set a high record at the top. Set 10. If you say 1, oh my, yeah. All right. So on average in my class, we are sitting here, right? Still good. No, robotic class is it pretty difficult? Oh, I have to confess something. You want me to confess? No? Okay, good. See, you're so eager to secret my secret, to hear my secrets, right? Well, no, it's not about me. Robotic, yes. You guys, right. Robotic itself, you go and ask some. In electrical, normally we don't have robotic. That's first. For mechatronic people who you are, and for mechanical, if you go and talk to mechanical people, they think it's pretty much difficult. Why? Why they think it's difficult? Because of connection between all these things we have. In this class, we by no way we are not talking, as the high-end robot, teaching in undergrad or grad class. In grad classes, many of these calculations, because they go deeper in mechanical side. Well, for us is just we limit ourselves to to a robot with 2 joints, basic calculations with matrices. We are not going down deep. But your feeling is right. Your feeling is right. I had that feeling too. That robotic is a deep water. If you won't be careful, there are big sharks in there, and have to be careful with what we say, what we do, because this is a part of engineering in which different areas join together: mechanic, solid mechanic, and just dynamic of the solid mechanics, and electrical and control. They join, and recently computers as well, and recently other things as well coming in. They join together and create an area which is very, very, very useful in engineering. Out there you see application of robotic, but the mathematical and the physical basis need study. I'm with you 100%. I also think that robotic can be difficult, but for our class, honestly speaking, so far I haven't seen any big issue which stops us to work and to understand and to enjoy the class. For people who are familiar with robotic, it will be kind of better understanding of what they've been doing. For people who are not familiar, these can be used as a basis to have an understanding if they get to this market. Well, I hope so. I hope everything will be good for you, but my confidence is yes, I agree that some part of it can be difficult, but we try to keep it in a lower lower level of difficulty, or at least I try to explain it in that. Okay, so let's see what comes next. Dynamics. Okay, let's talk about dynamics. When we talk about dynamic, means that we talk about force, movement, which means V, A, and definitely mass, and most likely time. So actually, dynamics means we are connecting everything now together. We try to look into our robot when it moves, when I'm applying force and it starts moving. I also can relate that to energy as well. Can relate it, right? When I have force, when I have movement, when I have mass, when I have time, energy also can come in, power also can come in, and all those other parts. But we focus on basics here. We focus on basics. So, and for a very, very simple example, remember, this is the simplest robot you can get. A two-link robot, RR robot, rotational, with angle theta 1, angle theta 2, with length L1, L2. As you can see, with length L1, length L2, theta 2, and theta 1. I focus my discussion on that. And this time, I need to consider mass as well. To understand that, mass of the link is distributed over the link. So when I have a robot arm, whether it's the plastic or aluminum, very light, or cast metal or steel or anything, whatever you consider, the mass of your arm is distributed for that. And when you apply force, it starts moving based on your mass and size, right? But again, to make it simple, to limit our discussion, we consider our mass as a point. That makes it very, very simple compared with the original shape, right? So we consider a mass of M1 centered at the center of the link, okay? Centered at the center of the link. So if it's L, it's centered at L over 2. Same for the second link. So I have, in this case, what I get is I have massless, I have very light links like this, like this, like this, and this, with masses located in the center of that link. So why are we doing this? For simplicity. How valid is this assumption? Well, not bad, but we have to be careful that what we are doing is oversimplified case of the original one, okay? But still good for understanding, still enough. We limit ourselves in that. We are not going further in this class, so that will be the main approach of our calculation in this class, okay? But how valid is this? Not bad. It's because if the link is symmetrical, more or less, so center of the mass, well, yeah, falls around center of the link, okay? And your calculation, torque and force and movement can be explained, okay? Everyone is okay with that? I hope everyone is fine with it. Otherwise, you have to go ahead with no assumption and do calculation in a way which can be much longer and more difficult, okay? So with this assumption, now we have new measures, okay? We have new measures. So what do we have? We approximate the segment point mass M1 and M2 located in the center, in the midpoint of rigid but otherwise massless rods, okay? Like this. Like this is what I have. Here is massless, but rigid, but I have a mass center here, okay? Let R1 denote the position of point mass M1 with respect to the first joint. So I consider this length as R1, which is halfway to the end of the link. M1, respect to the first joint, which at the origin of our coordinate system. Let R2 denote the position of the mass 2. So this length is R2. So I'm making assumptions. Calculations will come later, but appropriate assumption will make my calculation easier, much, much easier to understand, which is at the junction of the second. Okay, everyone's fine with this? Any question? So, is there any question? Yes or no? Okay.
No.
All right. So I need to see what is this? What does it mean? This silence on the other side. Are you guys just all right? Let's have a look at basic physics. Basic physics. Okay. The point mass m1 and m2 are acted upon by the force that are transmitted by the massless rod. Very obvious. As well as by the force of gravity. Yes, that's also, you know, a robot arm. If you don't apply any force, it just drops, right? Because we have mass and we have to consider that. We cannot ignore it, specifically because some of these robots are made to lift something, to carry something, so we have to calculate that. Newton's law claims that the vector sum of all the forces acting on a particle is equal to the product of the particle mass and its acceleration. So it's not just in robot. If you have an object on a surface, okay, and you apply a force F, if object has mass of m, it will be accelerated, in which that acceleration is your force divided by mass, and both are vectors. Okay, so if you apply force to an object with mass m, same thing here. So you apply a force. That force, which is that force is collection of all forces applied to that point, means gravity, or movement, everything together. At the end, it will cause some acceleration, some movement in our robot, and that's all. That's all. As I said, dynamics about, right? Moving parts, moving because of the forces. Where the F1 and F2 represent the sums of the forces, for example, forces of the rod, force of gravity acting each of the point of mass M1 and M2, while A1 and A2 are either accelerations, are their accelerations with respect to the origin of the coordination system. Okay, so is it difficult so far? I don't see any difficulties. Just, yeah, we knew that. We already knew that. Newton's law. You apply force, your object will be accelerated. How much accelerated? Force divided by mass. In what direction? In the same direction of your force. Very obvious, very simple. But when I talk about acceleration, this acceleration also can be can be related to the location, to the change of location. So let me go back to the figure I have. So let's say I apply a force and this mass M1 starts moving. How does it move? If you if you write down how this mass is changing, and consider that as a vector like R or R1, so location of M1 represented by a vector of R. It can be, you know, in Cartesian system, in polar system, whatever. This is location of R1, of mass 1. So the acceleration of mass 1 as a vector is related to that location. How is it related? As I said before, it's the second derivative of location and time. So it will be R1 dot dot, means second derivative of that vector. So the position of M1 with respect to the reference frame origin is given by R1. R1 is a vector, right? It's a vector. It's You can consider that as a set of coordinations of the points when it moves. Track of the mass when it moves, right? While the position of M2 is given by this. Well, this one is R1, right? Position of this one is this R, right? When you look at this R is summation of I'm getting called from Sierra Leone. I've never been. These days, it's probably can just stop everything. So look at this vector. This vector can be found by adding this vector together. So 2R1 plus R2. So this is location, sorry. This is a location of the second mass. Location of the second mass. So when location of the second mass is this R, acceleration of the second mass also will be second derivative of that R, which will be second derivative of this, means 2R1 second derivative plus R2 second. I'm trying to break down problem into simpler steps. I'm looking for acceleration to figure out forces, and for acceleration, I use a location of the mass, second derivative of that location, and to find that location, I just look into these simple vectors. R1, which shows M1 location, and R, this is R1, and this is R. And R for the location of the second mass. R1 simply is noun, and R can be found by twice of R1 plus R2. That's why you have acceleration of mass 1 can be found by second derivative of R1, and acceleration of mass 2 can be found by twice of second derivative of mass 1 plus second derivative of mass 2. Okay? And that makes sense, right? That's because you know that, I go back, you know that how this thing moves depends on its acceleration versus its joint and how this joint is changing versus the first joint. See, the mass of the end effector depends on how, okay, the movement of this end effector depends on how all the joints in series to the base are moving. This is not moving. This one is not moving. Fixed, right? This one is fixed, not moving. So this one is fixed, but you can find movement of the first joint versus the second joint versus the first joint, and the mass versus the second joint. That's why you see two vectors here. You see R1 and R2 all contributing to the acceleration of the mass 2. Now R1 and R2 represent rigid rods, again, as I said, so their lengths are fixed. Therefore, these vectors can be rotated. Okay? Can only rotate. But thinking. So in this class, we limit ourselves to robot, this two-dimensional robot, which is R, right? But someone can come back to you someday in future and tell you that, I don't know, probably in another class somewhere else, say, okay, you remember this two-joint robot you use? Say yes. So I have a translational link in between, okay, which means this length also changes. In that case, you have another parameter, which is D, or this chain, which will be added to this R1 here and makes everything different. makes everything different. In our class, we are not considering all those, but you have to be careful, and there is nothing scary with robots as well. As long as you can write down step by step the location, then derivative, then move to force and work. If you know how to do it step by step, you can do the analysis. Analysis is not difficult, as long as you won't get lost with the equations. I want to move forward and see what else we can do. Now, from these accelerations, which are in abstract form, you see there is no, I don't see effect of theta or anything else here. I just have very highly abstract model of my acceleration, okay? But there is a point here. It says this acceleration, these are vectors, right? This acceleration, since the length of joint is fixed, so it only can result in rotational movement. So when I talk about acceleration, acceleration is for the object which rotates. When I talk about rotational mechanics, I have to remember that many different things might happen compared with linear mechanics. In linear mechanics, simply you have a line of movement back and forth. That's it. And your acceleration can be in any direction. In linear, even 3D, three-dimensional space, your acceleration is just simply acceleration you see. But when it comes to rotation, you have to consider other things as well. Why? Yeah. If you let this object move naturally, if there wasn't any link, if there was no link, and if you had mass m, there is no link, okay? There is no link. If I move it, if I apply a force, what happens? This object starts moving in the direction of the force. It gets accelerated. That acceleration, the value of acceleration will be the value of the force you're applying divided by f. Pretty simple, right? That's if I don't have any link. What if I have a link? If there is a link, what happens? Does your object continues moving outside the line directly? It goes away? Does it go? Does your object continue moving on straight line in direction of f? What's the answer? Yes or no?
Right.
Definitely not. Definitely not. What happens? What happens? Although you're applying the force in direction as you have, something else comes in, exactly as you said. Something else comes in and starts. Well, since this mass can't go away, the only way of movement for it is just rotating around this center. It's like something else, another force, another acceleration is applied to that mass and change the direction of the f continuously. This f originally was in this direction, but it becomes in this direction, then it becomes in this direction, and then it becomes in this direction. Something continuously applies a force, an external force, actually because of the mechanic, because of the structure, and change the direction of the force continuously. And you know that from your experience that if I have a force in one direction, if I want to change that force direction, I have to apply another force. I have to apply something else, right, to change the direction. That's why in this case, since I have rotational movement, my acceleration will be in two components, in two directions actually. I have my acceleration can be decomposed into main components. What I call it radial, and the other one is tangential. Okay, tangential and radial. One of them is well, when I have this movement, if I use this, okay, this is an object, this is the mass, and this is a joint. When I'm when I'm turning this, when I'm starting moving this and getting by applying force, it gets accelerated. One force is in the direction of just well, one force will be applied to keep it on circle, on circle. How much is this acceleration? Depends on two parameters. How long is the length? We all have done that since childhood. When I have a heavy thing connected by a rope, when I start rotating that thing, longer it becomes, the stronger it becomes. Just becomes stronger when you make it longer, right? When you make car longer, it depends on and also how fast it's moving, and it's onward. There's a force, there's acceleration applied by the system by this rigid rod. This rigid rod. If it was in spring or something elastic, it would, expand. But since it's rigid, it applies a force to keep it in line with the direction of direction of the rotation on the circle. The other component, which is tangential, is the acceleration against same structure. If I try to reproduce it, okay, is the acceleration you have like tangential or just trying to rotate that in that direction. So my acceleration has two components, and this is a very, very important issue in every rotational mechanic, every system of I always ask if I have high school students, or sometimes people who are new to physics and mechanics, I tell them, can you explain why when you are biking, if you stay and not moving, why your bike falls? Why you can't keep balance if you are not moving? Why it's easier for someone who's biking when they're biking, as your bike just stays. You don't need to apply any force. It's very easy, it stays, and you keep balance of yourself. But when you reduce the speed, or when you stop, you can't do that. Think about that. Why? Why? Because of these forces, this acceleration. This when I have this tire of my bike rotating, when it's rotating, it creates a sort of inertia which has a direction perpendicular to the plane of the tire. And if you want to change the direction of that, you have to apply force. That's why you see bikers, motorbikers, when they want to turn, they have to push, they have to apply some force to make their bike bend because they want to change direction of that vector of rotation. We don't have that in linear movement. In linear movement, if something is moving. We don't expect anything like this, but in rotation, there are other components we need to consider. So, in short, acceleration now has two components. So, what I had here, I have to decompose this into components as well to write the equation. So, my acceleration has a radial and tangential component, tangent and radial components. The radial components is negative omega to the 2r, and this one is alpha cross a, cross multiplication. Here I didn't explain that. Yeah, I had to. Of the vector of the angular acceleration, which is perpendicular to the plane of the motion. to the plane of the motion. So it comes out of here. So if I go here, you see this is alpha. Again, right hand rule. If you have acceleration counterclockwise, it's out. If you have acceleration clockwise, it goes in. This is cross multiplication of r and vector, two vectors. And I hope you remember cross multiplication in vectors. When you have cross multiplication in vectors, I just write it down once for you to remember. Well, I know you know, but if your alpha is alpha x I plus alpha y j plus alpha z k, and your r is r x I. These are three-dimensional vectors, right? Well, our case is two-dimensional. I understand that, but I want to write it in three-dimensional in case you need it. So r y j plus r z k. I have alpha times a cross vector multiplication. For vectors, we have two or three times of multiplication. Scalar multiplication means you have your vector and a scalar number multiplied by all components. We have dot multiplication and we have cross multiplication. Okay, cross multiplication is the largest one or more complicated one. Alpha times r becomes a determinant I j k, you put them there, then goes first vector, which is ax, components of the first vector ay, a, and components of the second vector, which is rx, ry, and rz. You find the cross multiplication. For two-dimensional, it's easier. For two-dimensional, it's easier if I remove this. Well, I'm sure you have it as a reference in the video. If it's two-dimensional, I don't have these z components in z components. Therefore, alpha times r gives me the same thing if I follow the same j, first component, which is alpha x, alpha y, and rx, ry. So when we do for three-dimensional, this one is even easier. I don't need that, sorry. For this one will be much easier. So you have a multiplied by r in the direction of right hand side rule. So a times r, it gives me tangent in this direction, right hand side. This one, okay, multiplied by r, one direction to the other one, gives you the tangent of the circle, which is in this direction. Okay, so the values multiplied in the direction of tangent of the circle. Okay, and the second derivative with respect to the time of the vector r1 and r2. So this is one side of the equation. This is one side of the equation. I'll come back to that, right? But the other side, when you talk about r and r2, second derivative, therefore, will be a with this or this, and right hand side, depending on what is the diameter of the circle of the movement, will be for first mass. If you remember, it was r. For the second mass was, this one was r1. For the second mass was r equal to 2r1 all vector plus r2. I hope you remember that. We did this. Now we are replacing things based on this equation. Acceleration of the mass number 1 is calculated as this, and acceleration of the mass number 2 is calculated as this. Now we have both derivatives. We put them here, and we get some calculations. Let's see what we get. For robot segment rigid bus, we have R1 equal to theta 2, the second derivative of theta r, second derivative of theta 2. This is acceleration of the rotational movement of joint 1. Same here, and this is sorry, my bad. I couldn't see. This is speed. If you look at this here, this is rotational speed, which is first derivative of theta, and this is rotational acceleration, which is second derivative of theta. Same goes here. So if I write them down, first derivative of theta, second derivative of theta 1, first derivative of theta 2, and second derivative of theta 2. Oh, sorry, theta, not theta 2, which theta 2, theta is equal to theta 1 plus theta 2, as we have here, okay? And graphical explanation that how these vectors are calculated or can be, if you want to make an imagination understanding, graphical understanding, it will be like this. And based on this, you can write down the forces now. The force for F1 is M1A1, for F2 is M2A2. Okay, and if we replace these forces, if we convert these forces, if we calculate based on these forces torque at each joint, we have to multiply by the distance of the force from the center. So this was the mass, center of mass. This one was the center of mass. This force was here. So the torque will be this length, which is R1 by 4, R1 by force 1. And for this one, if you remember, we did the calculation, which was R, which is 2R1 plus R2 by the force F2. So force F2, which is M2A2, is R will be this. These will be torques at two joints, and if you replace them with the calculation, you see torques at two joints will be this. For torque number 1 will be mass number 1, length to the 2, theta 1 to the 2 in the direction of K, means Z. And for the second one, it's calculated, as you can see, depending on the structure and the size of the arms, and also mass of the arm of the robot. Okay. I guess we are running out of time. I don't want to continue, and I don't want to go too fast, and I won't be able to explain it. Next week, I come back again to same point. Please go through and have a look at it and see if you have question or you have difficulty in understanding this. You have the slide. I'll be more than happy to discuss that next week. Okay. Now, before we leave, just again, in the scale of 0 to 10, in the scale of 0 to 10, how easy was this dynamic part? Level of easiness. So it was 9% easy. It was 9 So very busy, mean, huh? Do you still say 9? So good, very good. Okay, so it's hard to tell until we do examples with values, Henry. Yeah, that's not smart. Yeah, not easy. 99 for Paul,
It's all
you didn't
about
listen to
practice,
me. I said
practice.
how easy. You're saying it's very easy, right? Okay. All right. So I understand. That's not just you. That's not just us, me in this class. So far, it's the hardest part of the class. Dynamic it is. Dynamic is hard. Not because it's complicated to understand, because as I said, we are combining different things together, and final exam will be lots of substitution. It looks like easy to make small mistakes. Well, hopefully not. I'll try to not to count on small mistakes. Uh, Engineering, more than everything else, we need understanding. Understanding is the most important, and numbers are just tools to evaluate that understanding. Unfortunately, we don't have any better way to do it. So that's why we use numbers, but hopefully in the final, we won't have, it's impossible to say we don't, we definitely will not have, but I'll try to make it, reasonable between calculations and understanding as well. So I stopped recording.